Let's talk about graphing of the exponentials. So if we have your basic exponential function like this, 2 to the x, let's go through and get an idea about what it looks like. So if I plug in 0, so I have 2 to the 0 is 1, which is logical, I hope. If we plugged in a 1, we'd have 2 to the first is 2. If we plugged in a 2, 2 to the second is 4. If we plugged in a 3, 2 to the third is 8. If we plugged in a 4, 2 to the fourth is 16. We plugged in a 5, 2 to the fifth is 32. So you can see it's getting big really, really fast. But over here, if we plug in -1, we get 2 to the -1, which is 1/2. Okay. If I plug in -2, that's 2 to the -2, which is 1/4. Oh, 1/4, eh? If I plug in -3, so that's 2 to the -3, so 1 over 2 to the third, so that's 1/8. 2 to the -4, I think you get the idea now, so that'd be 1/16. 2 to the -5 would be 1 over 32. So when I'm going to the left, as x is getting negative, these guys are getting smaller and smaller and smaller. But, and we've talked about this a lot. We have talked about this a lot. See right here, I've got 0, 1. So what's happening is I've got that 0.01, got that 0.01, and then it goes to 2, but then it goes up really fast. But over here on the left, -1, like 1/2. So it's decreasing to 1/2, then 1/4, then 1/8, blah, 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 blah. But it's going to decrease like that. And hopefully what we notice is that, wait a second, there's no way this can ever actually equal to 0. This will always be 1 over something. These numbers are getting infinitely small. What this amounts to is these guys are going to, the denominator is going to get infinitely big, and the numerator is going to stay at 1. So they're getting infinitely close to 0. We're going to end up calling this a limit later. But right now, we're getting infinitely close to 0, but it never equals to a negative. These y values are never negative. These y values are negative, never negative. So this is our basic graph right here. And you can see that it starts small and then it increases. This is what we call increasing exponentially because our variable's in the exponent. And this is what we would call exponential growth. So exponential growth. And then just for the record, if we turned it over, if we said something like y equals 1/2 to the x, you're thinking, well, that's the same thing as 2 to the -x. So if I did that, if I did 2, if I put in 0, I still get 1. But if I plug in 1, that becomes 2. Oh, that becomes the 1/2. And then if I plug in 2, that becomes, so it basically flips everything. So everything is flipped. So if I plug in -1, that would become 2 to the +1. If I plug in -2, 2 to the positive, blah, blah, blah. So basically everything's flipped. So the graph ends up looking like this. So it starts out big, but then it gets smaller and smaller, approaching 0, but never actually equaling 0, never actually equaling 0. It's getting smaller and smaller, but never actually equaling 0, never becoming negative. So this is what we call exponential decay. And this is going to come up, when we get to the word problems and stuff, this is going to be an issue. That's all going to be in the calculator part. So that'll be after spring break. So if we did something like slapped a negative out front, if I said, okay, y is equal to -2 to the x, see, the negative is not with the x power. The negative is not with the x power. So all we're basically doing is we're turning everybody negative. So we're just flipping it over like that. So if we put a negative out front, we're just flipping over. We're changing everybody to a negative. So we're just flipping it over. Similarly, over here, if I slapped a negative out front of that, 1/2 to the x, same situation. It flips it over. So it would look like that. Okay. So not too big of a deal. Not too big of a deal. Not too big of a deal. But here's where it is going to get to be an issue. When we start shifting left and right and up and down. So this gets into the good old HK form. And I know you saw lots of HK form back when you were in Algebra 1 and Algebra 2. And we did a little bit of this when we were graphing trig functions. So A is our base. H is the left-right shift. And K is our up-down. Okay, so H is the left-right. So H is the 0 of the x minus H part. So what we need is an example of this. So pause for a second. Okay, so let's do one where we have a shift here. So if we think about, this is our standard form here, and we're just doing 2 to the x. We could do anything here. So good old 2 to the x would look like this. Well, see, now I've got a shift right here. And based on what we said earlier, H is your left, right. So H would be the 1. And somebody says, what are you talking about the 1? It's the 0. We would say, uh-oh, well, x minus 1 is equal to 0, so x is equal to 1. So see, our new center, and I know this is probably in the best terminology, but see, our new center is going to be that 1 because it makes a 0 in there. Because that's going to make 2 to the 0, but then you have that 3 in there. So 2 to the 0 is 1, plus that 3 makes 4. So check this out. What did this guy do right here? This point here in the center, this guy is the center. See, there's our center point. And now here's our center point. Well, look at this. 0 to 1, that's 1 to the right. And then 1 to 4, that's up 3. So this went up 1, right, 3, which kind of matches what I said just a minute ago. The H is our left, right, the K is the up, down. So I think I've alluded to this a few times that we love HK. So what we're going to always ask you to do is do at least 3 points. So I could say, well, I'm going to plug in 2 then. Here's my center. Here's what I always recommend. Do at least 1 point to the right of the center. So if I plug in 2 to the first plus 3, that makes 5. Then we need to plug in 1 point to the left. So I'm going to plug in 0. If I plug in 0, that's 2 to the negative 1 plus 3. Well, that's 1/2 plus 3, so that's 3.5. So we're always going to want at least 3 points. Never hurts to do more. So let me see. If I plug in 3, that would be 2 squared plus 3. So 7. If I plug in 4, that'd be 2 to the third plus 3, which is 11. If I go over here and plug in negative 1, that'd be 2 to the negative 2, which is 1/4. So that'd be 3 and 1/4. If I plug in negative 2, that'd be 2 to the negative 3 plus 3. So what do you know? That's 3 to the 1/8. So wait a second. What's happening here? 3 and 1/4, 3 and 3/8. If I plug in 3, that's going to be 3 and 1/16, because that'd be 2 to the negative 4 plus 3, which is 1/16 plus 3. So wait a second. On this problem, and I actually forgot to mention this. I should have mentioned this. This is a big deal. This guy is approaching 0. This guy is approaching 0. So it has an asymptote at y equals 0, because the y value is getting infinitely close to 0 on the side like that. Same thing over here. The asymptote is y equals 0. It just we're on the right side this time. So we're getting infinitely close to 0. So the K value, K is the horizontal asymptote. K is the horizontal asymptote. So if you look at this, you're saying, well, wait, that seems logical because these values are getting closer and closer to 3. So 1, 2, 3. So here's 3 right here. See, that's going to become my new asymptote right there. And then this guy was my new center point. So 1, 4, that's kind of like my new center point, even though it's really not in the center. I get it. It's not in the center, but that's what I always think of it as. So my new curve would look something like this. So that would be my y is equal to 2x minus 1 plus 3. So A is the new asymptote. Your horizontal asymptote is y is equal to 3. K becomes the new asymptote. So that's a big deal. So basically, we just took this guy, we shifted it right 1 up 3. And like I said, we are going to ask you to show 3 points every time, every single problem. So I would, what the zero of the exponent ought to be the center, and then at least 1 point to the right, at least 1 point to the left. And that's how we're going to graph our exponentials. That's the plan.